So that seems to work.
Okay, seems to work.
There we go. All right, so welcome everyone to the second Geo.X seminar. So I'm happy to present today Mark Panning. Mark is from the Jet Propulsion Laboratory in the US. Mark did his bachelor in geological sciences at the Indiana University and then finished his PhD in geophysics at UC Berkeley. He then remained as a postdoc at the Berkeley Seismological Lab till 2006 and worked then at Princeton University between 2006 and 2008. And between 2008 and 2017, he was assistant professor at the Department of Geological Sciences at the University of Florida. And since 2017, he's a research scientist at the Jet Propulsion Lab in the US. What I also wanted to mention here, so Mark is the project scientist and co-investigator on the InSight mission to Mars, and we will hear about this during this presentation today. He's also a co-investigator on the Dragonfly mission to Saturn's moon Titan. And he's leading the Farside Seismic Suite that was selected in 2021 to fly seismic instruments to the moon, to the far side of the moon. And I guess we will hear also about this today. So without further ado, Mark, please, the floor is yours.
Thanks, Ina. I've officially been at JPL 5 years. I just got this plastic 5 in the mail while I was on vacation last week. So officially, I have been at JPL 5 years now. So today's talk. I'm going to talk for the first 2/3 or so about Mars, and then the last 1/3 about prospects for the moon. Mars is more interesting right now because we've got data. The moon is, we're waiting to get that new data. I'm on this title slide, I only list myself because I'm the one presenting, but the next slide has, if I can make it move. This was as of March or so, everybody on the InSight science team. If you look very carefully, I'm sure Ina's name's on there somewhere in the tiny print. Really, all of this is just to say that I'm not going to make you read through all these names. This is really just to say that this is really a massive project, and everything I'm talking about, I'm presenting the high-level discussion that's a result of tons of work from all of these people. So I just really want to emphasize that. And so for those who aren't familiar with InSight, who haven't been living and breathing it for the past, I don't know, I guess now it has been about 14 years. I've been doing InSight stuff for everybody else. The exciting thing about InSight is it was a mission to Mars. It still is a mission to Mars. Was the first one to really try to look at the interior of Mars. There's lots of missions to Mars, and they mainly focus on the atmosphere and the surface. And I love the atmosphere and the surface. There's great things to study there, but I'm a planetary geophysicist, so I want to know what's happening on the inside. And so this is InSight's really just trying to recreate the basic work we did on interior geophysics on the Earth and the Moon in the 20th century. So, on the Earth, we had asked these questions. How thick is the crust? What's the mantle look like? Size and density of the core? Where do quakes happen? What's the heat flow? And these are all questions that were addressed mainly in the early 20th century for the Earth, and of course continued to refine as time goes on. And on the moon, once we had the Apollo missions and we started getting data back from the moon from 1969 through 1977, we were able to do much of the similar stuff, and the retroreflectors are actually still getting data. And so, that was the middle of the 20th century, and now at the relatively early part of the 21st century, we're finally able to do the same thing for Mars, to look at these big scale processes and the big scale structure of the interior of the planet. And so, in order to do that, we had 3 primary instruments. I'm going to talk mostly about size because I'm a seismologist and that's my bias. So that's mostly what you're going to hear about today. But we are built on using all three of these instruments. So we have the seismic instruments, which hidden under a wind and thermal shield here. I'll talk more about that later. But we're also doing radio science with the two X-band antennas here, which point to the east and west, and can do communication direct to Earth in either the morning or the evening, depending on which antenna you're using. These let you do very precise radio tracking to look at things like nutations. I'll talk about that in a bit. And then the last instrument, which I'm going to talk about briefly, but I'm sure many in this audience know quite a bit about because of its connections with DLR, is the HP cubed heat flow and physical properties probe. This was designed to reach 3 to 5 meters and also includes something that you can't see, which is a radiometer, which is looking at the backside of the lander. And that was designed to measure heat flow. But it's a very capable thermal properties probe. In order to support those main instruments, we have lots of auxiliary instruments that are doing a lot of science in their own right. We have cameras on the arm, a camera on the arm and a camera under the deck that are taking lots of pictures. We've taken, Justin Mackey always shows pictures and I've forgotten how many pictures it is, but it's thousands of pictures between the two cameras. We have a magnetometer sitting under the deck, which has done some really great science. The arm itself has a scoop, which has done soil property work. We have a weather sensor, twins out of Spain. We have a pressure sensor, which is sitting right in the middle of the deck. And all of these have done a lot of great science in their own right, which I'm not going to talk about as much as I should here because I want to focus on the seismology because that's my thing. But there's quite a bit of quite a bit of interesting science that happens because of these sensors that were originally designed to support the three major instruments. So we landed on Mars in 2018, in late November of 2018. We are situated right here in Elysium Planitia, a little bit north of where Curiosity Mars Science Laboratory is roving in Gale Crater. And this was where we chose to land because we needed to be near the equator to have solar power, and we needed to have it smooth, flat, and boring so we could land safely. And once you added up all the things we needed for safe landing and long-term operation, this was about the only area we could land. Here's a picture of us from the high-rise camera in orbit. I love it when missions talk to each other. So this is one mission observing another mission. You can see actually from orbit, our two big solar panels here, and this really bright pixel right there is actually the seismometer placed on the surface, and it has that reflective, at that time, very reflective wind and thermal shield. Now it's pretty dirty, probably wouldn't be as bright now, but this was relatively soon after landing. I'm going to briefly talk about the other major other instruments, but I just wanted to give a quick introduction to them. So RISE is our radio tracking experiment, rotation and interior structure experiment, I believe is what RISE stands for, although I forget my acronyms at times, so don't worry if you don't remember them either. So this is basically looking at the precise spin axis measurement by looking at the velocities as we may do direct Earth transmission. Early on in the mission, we did hour-long communication sessions to do this data gathering through most of the first extended mission, which we're finishing up now. It was mainly half-hour sessions, and now as energy is getting tight, which I'll talk about in a bit, we're doing 5-minute sessions where we can. What this is looking for is looking at the change in the spin axis, which it relates to the very long change in the spin axis, which is the precession, which takes 165,000 years, and then these shorter wobbles around it, which we call the nutations, which are durations of a year or less, a Mars year or less. Those are the kinds of small changes in the spin axis that we're looking for. The data, once you've looked at it, has done some some key work. It's reconfirmed that the core is liquid, and has also determined the radius of the core very consistently with what I'm going to talk about later, with how the seismology determined the radius of the core. We also have a magnetometer, the InSight FluxGate magnetometer, IFG, and it's been made lots of measurements early on in the mission, and then occasional measurements throughout the extended mission. Some of it's looked at both the constant field, the crustal field, which is the crustal remnant field, and the time varying fields. The crustal field, one of the interesting observations of the crustal field is about 2000 nanotesla, which is 10 times larger than what's observed from orbit. That's not saying the orbital measurements are wrong. It's telling you that the crust is varying on length scales that are small enough that they can't be measured from orbit. So this is telling you about the small length scale measurement variations of crustal remnant magnetism on Mars. And using the different periodicities, we can start looking at an internal structure of the electromagnetic structure. There's still ongoing work on that. And there's lots of work at looking at how the magnetic field variations are associated with solar wind and ionospheric variations. So there's a lot of science to be done there. Meteorology, I'm showing, this is a very early slide. There's so much more that I could talk about here. This is actually the best more or less continuous weather station on Mars, and there's a wealth of data here, but lots of atmospheric waves, a near infinite number of vortices, dust devils, if you will, although we've never actually seen one holding dust, so maybe most of them are dustless devils. Unfortunately, none of them have cleaned off our solar panels, but there have definitely been many thousands of them recorded by our pressure sensor. Waves of all sorts of times, infrasound waves, atmospheric gravity waves, all sorts of very interesting structure. And then, of course, we have now about 2 Mars years of data to look at annual and interannual variations. So now zooming into, my instrument of focus, which is the seismometer. What's really interesting about doing seismology on Mars is you really need extremely high sensitivity. The very broadband seismometer provided by CNES is extremely sensitive. Its target was 2.5 times 10 to the minus 9 meters per second squared per root hertz. Not that anybody knows how to visualize that, but if you put that in displacement in our frequency band of interest, we're looking at displacements that are on the scale of a hydrogen atom. And the actual sensitivity was actually ended up being better than our target. We under-promised and overperformed, which is what you want to be able to do. But in order to get that level of sensitivity, you really have to compensate for all the other noise sources. And so, that's one reason why we have all of these other sensors on there, is because we need to, a seismometer is really good at measuring lots of things besides just ground motion. It's a great thermometer. It's a great wind sensor. It's a great magnetic sensor because of the magnetic properties of the spring. So we have to know all of these things. So we get to Mars, and this was on landing, or very soon after landing day, the first lander selfie, and look at those beautiful clean solar panels. We'll get back to that later. They don't look like that at all anymore. And this was when SEIS was on Mars almost. It was still actually a meter off the ground. And this is very similar to what Viking landers did. They had a seismometer that stayed on the deck, and it very well measured how the deck rocked in the wind. It was unable to convincingly measure any seismic motions of the ground. So we had spent a long time getting this onto the surface, and I'm going to just kind of briefly go through this video. So this is just showing the deployment. The sols are counting up in the corner, and you can see we put SEIS out on the surface, out a little over a meter away. And then a little bit later, we're going to release the tether and do various leveling of the seismometer. And spend a long time opening this thing we call the load shunt assembly. It took a long time. The idea was to try to decouple the seismic sensor from the tether changing in the temperature changes during the day. And it took us I think about a month to actually get that thing pulled open, which sounds crazy, but everything is hard when you have to send robots commands and wait to see the results. And eventually then we put the wind and thermal shield on top, and then on Sol 70, the grapple releases, and now we have a fully functional seismometer that's doing what it's supposed to do. So 2.5 months or so to get that deployment. That was a long time for something that could take you maybe 2.5 hours on Earth. But that's the joy of working in space with the slow communications. So at that point, we've got a functional station, and it's as I said, very quiet. It's actually the quietest seismic station in the solar system, because on Earth it never gets as quiet as we get on Mars because of the oceans. And so we are able to do some incredible stuff on small events pretty far away. One of the big questions we had when we were first selling the mission is how well can you locate a Marsquake with a single station? People are always taught that you need to triangulate. The short answer is no, you don't need to. You can get distance, which everybody learns in intro Earth science classes somewhere in their lives. You have two different kinds of waves, P and S waves, and the timing difference between them tells you the distance. So this is an example of a quake, and we look at the time difference between them and get the distance, but the direction is actually also shown here because we can look at the polarization of the waves. And so if we look at the polarization of the P wave, it actually points in the direction that the source came from. And so if we have distance and direction, we have a location. We aren't able to do that for all of our quakes. If they're small, we don't get good polarization, but we can still often get distance. To put it in scale, this is every event we've recorded. There's over 1,300 events on here. All these colored symbols on here are events. What I'm showing here is basically the entire mission's worth of data. Each horizontal line on this chart is one sol of data, one day on Mars. And the color scale is such that the purple colors are times when the noise is low, and the warm yellow and orange colors are when the noise is high. And this is going from midnight to midnight in local mean solar time on Mars each day. The gray lines show sunrise and sunset. And you can see Mars goes through a very regular diurnal set pattern that has a seasonal modulation on it that's very predictable, actually. You can see here this long, quiet evening period that happens, which is where we record most of our events. And then during the dust storm season, we don't get that quiet evening time. And then we're back in the dust storm season now, and you could see a very similar pattern to what was shown in the last dust storm season. There are 2 3-week gaps here. One was due to conjunction. And the first year, we actually could have saved data during conjunction, but we went into safe mode just before conjunction and couldn't get back out. So we had to be in safe mode through the whole conjunction. And then this one was a dust storm early this year in January. And now you can see lots of gaps here at the end because we're going into an intermittent recording mode to save energy. Our first large event was a magnitude 3.7, which on Earth we would not call a large event, but it was the first large event that was very clearly seismic on Mars, and we were convinced that what we were looking at was real data, not just noise. And you can see the P&S wave right there, and you can also see one of the other things we see in our seismic data all the time, which shapes so much of what we see, which is glitches. These are little pops and cracks that happen mainly because of temperature changes near the sensor. They're something we have to deal with. They're also very common in the Apollo data as well. It's the joy of working on an installation that's sitting out on another planet. On Earth, we put things in nice temperature controlled vaults to try to minimize all of these things. On Mars, we have to deal with them. So this happened on Sol 173. So that was another 3 months after we finally got everything installed. So there was a long period of time where we weren't sure what we were going to see as we finished off the dust storm season that was active when we were landing. After this point, we went into a nice long time period where we had quiet evenings and we recorded lots of events. And then we thought we were, after going through a second round of quiet seasons between the dust storms seasons that we're just now in another dust storm season now, we thought we were kind of done seeing big events. But then about a month and a half ago or so, on Sol 1222, Mars decided to reward us with the biggest event of the mission by a pretty decent margin. It was a pretty giant event. Relatively speaking, once again, magnitude 4.7 on Earth, we'd say it's a moderate event. You'd feel it if you were close to it. So that would be exciting. But on Mars, this really stood out. This is raw data, unfiltered, just what came down, the raw instrument counts. I mean, this is converted to ground velocity, but aside from that, it's totally raw data. And so you can see the signal to noise ratio is massive here. The noise record before the event just looks like a flat line, a beautiful PNS. Compared to what were until that point our two other biggest events, which were Sol 1000A and Sol 976A. The black lines are on the same scale, so you can't even see those other two events if I plotted them on the same scale. And the only way I could actually see them is to enlarge them. And here you can see all of these little spikes and everything that are showing up in the data. These are the glitches. The glitches are also present in 1222A. They're just small and you can't see them anymore. So I think that's exciting. There's going to be a lot of work done on this. I'm not really going to talk about it right now because it's work in progress, but we're putting together a special issue. We have approximately 30 papers expected for this special issue already. So there's going to be a lot to be done on this event. I'm excited because this is actually the first event that I can do some of the location methods I proposed for using surface waves that we never were able to do because we could never see them on the smaller events. But with this 4.7, we've opened up a whole new way of looking at Mars quakes. But even without those big events, we were able last summer to put out several papers that actually did the main things we wanted to do with the mission, which is constraining the crust, mantle, and core. So, this study led by Brigitte Nattmeyer-Indren and myself and others, we looked at the crustal structure of Mars. And so if you just have the PNS wave, you have enough information to look at the location of the event, but you've used up all your information, then so you can't look at structure. So you have to look at other small signals to try to pull out structure like crust, mantle, and core. And so in this case, we use something called receiver functions, which are looking at little arrivals that happen after the initial arrival of the P wave that represent converted S waves at various interfaces at depth. As of last summer, we were clear at seeing 3 arrivals, and those could be interpreted either as a 2-layer crust or a 3-layer crust. Following that, looking at other receiver functions on multiple on waves that bounced off the surface multiple times, we're actually now pretty convinced that the better model is the thicker crust model, the 3-layer crust model, which is about 40 kilometers thick under the InSight landing site. Which tells us that the overall Martian crustal thickness is closer to the 50 to 70 kilometer thick on average, with quite a lot of variation around that. We also are able to look at the mantle. In this case, what we look at are waves that bounce off the underside of the surface of Mars a few times, and that's our extra data that we're able to look at. These arrive just a little bit later after the P wave and S wave, as compared to the receiver function stuff, which is just after the P wave or just actually before the S wave. And with these kind of data, this is a paper led by Amir Khan. We're able to start looking at the velocity structure of the mantle. It tells us that the mantle has a thick lithosphere, 400 to 600 kilometers thick. At this, there are various different ways of looking at this, but a potential temperature in the 16 to 1700 Kelvin range. And there's a lot of interesting things to follow up on with that. At the same time, Simon Stahler at ETH led a paper looking at the core, and this was able to pull out small reflections of S waves off the core mantle boundary. He was that these groups were able to pull out this structure, these arrivals, by looking at the polarization of the data to really emphasize S waves that are coming up almost vertically under the station. So they're almost entirely horizontally polarized. And you can pull out SCS waves from several events. At that time, we were looking at 6 events. We've seen it in a few more since then. This was an exciting time because it showed that the core radius was over 1,800 kilometers, which is very much on the high end of our pre-mission expectations, not outside of our pre-mission expectation range, but at the high end, which also tells you that the core is not very dense. And there's a lot of work going on trying to understand that. It actually suggests we have to have a whole lot of light elements in the Martian core, possibly more than we think should be able to fit. There's a lot of work going on. If you just do it with just sulfur, which is what people have traditionally done in the past, it suggests very high concentration of sulfur in the core, which make geochemists uncomfortable. So there's work to be done there to understand that on what's happening with the light elements in the core. We're also looking at the seismicity. So this is very early work, just showing some of the first 3 events we were able to locate clearly. I only show this not because we actually have lots more studies now, but this emphasizes one thing that I found very interesting early on, and that held on through the missions, that we see lots of events in this one little area, Cerberus Fossae, which was very exciting to me, because this is an area that we suspected before the mission landed that we would see events from here. There's young, geologically young volcanism within the last 10 million years. There are rock fall trails that people interpreted as being from seismic shaking. And so this was a place we thought we might see Mars quakes, and sure enough, it's the place we saw the largest number of Mars quakes that we saw of any particular location. So this was something where our pre-mission expectations were upheld, and that's surprising. Usually we're wrong, right? That's so it's exciting when things like that happen. We can look at the overall seismicity. This is a kind of an old chart, but it's just showing the number of events as a function of magnitude. At this point, when this was made, we actually looked like we were looking pretty low on the big events, because we had kind of a deficit of events near magnitude 4 or above. But we've actually filled that in a lot in the last 400 sols, with 1222 showing up right here, and then several other big events that have filled in some of that range between magnitude 4 and 5 that seemed to be a deficit before the event, before those events that happened actually pretty late in the mission. I want to briefly talk about the heat flow and physical properties probe. This is the penetrator was designed to get up to 5 meters below the surface and measure heat flow by temperature sensors. Matthew Inman, the oatmeal creator, really liked the mole and made some really nice pictures of the mole. Didn't quite look like this, but anyway, it quickly got down to about 30 centimeters or so, and it stopped. And so then we did a lot of effort, pulled the top off, and then it did this where it backed out. That was painful. With a lot of work, we were able to use the scoop to push it down, including a tilted scoop to get it below the surface. And then at that point, we actually buried it and patted it down and hoped it would go. It still didn't go, but at least it got fully buried beneath the surface. And since it's such a capable tool for measuring thermal properties, we've actually been able to look at how the thermal conductivity varies through the course of the seasons. And it's telling us that actually the atmosphere plays a pretty important role in that. There's a significant portion of the thermal conductivity that's related to atmospheric pressure, so the gas phase and the near surface. But anyway, right now we are nearing, unfortunately, nearing the end of the mission. Over here in the lower left, you can see the selfie early on in the mission versus the selfie about 2 months ago or so. We've accumulated a whole lot of dust that covers our solar panels. And so our energy has gone from early on in the mission being up to as much as 5,000 watt hours per sol, to now we are cruising along at a few hundred watt hours per sol. And so we've as our energy has decreased, we've had to curtail our instrument usage. The fact of the matter is, over the course of the summer, we're likely going to get to the point where we can't keep the instrument on anymore. And we may, at that point, we'll deplete the batteries and go into something we call dead bus mode. I can talk more about that later if people have questions. So anyway, summarizing the Mars portion, lots of Mars quakes, and we really achieved what we wanted to do. The heat flow probe didn't get to where we wanted it to do, but we really got to the interior structure, and space is hard, so everything didn't work exactly as we wanted to, but we're actually very happy with the results. And I think there's going to be lots of work done on this data for likely decades to come. So I'm very excited to see where this all goes. Looking to the future, as was pointed out in the introduction, I was funded to do the Farside Seismic Suite, which is actually going to function. Hopefully, we'll be landing on the far side of the moon, and around 2025. We're working on the details of when launch and landing is going to happen, but it's a long-lived package that will sit on a commercial lander. So the commercial lander will die at the end of the lunar day, which lasts about 2 weeks. But we'll keep going for months afterwards, recording seismic data and communicating with a relay satellite to go back to the Earth. We are landing in Schrödinger Crater at about, we're going to be on the northern edge of Schrödinger Crater, is about 71 degrees south. There's a lot of interesting questions. Primarily, the Apollo observed quakes are almost all on the near side. And so this is the first observation on the far side, the most sensitive seismometer ever to land on the moon. And so we're going to fill in the gaps of what the far side is doing. And there are differences between the near side and far side at the surface. We know there are differences in the existence of mare. There's a difference in heat producing elements near the surface. There's a lot of differences that may relate to differences greater at depth where these events are happening. So there's things we want to know. We're also going to look at local structure in Schrödinger Crater, which is a beautiful impact basin. And by getting the most sensitive seismometer, we're actually going to try to determine the noise floor on the moon, which is related to micrometeorite impact rate. So lunar seismology is challenging. Here's an earthquake and a moonquake, both in a 1 hour time scale. They don't look at all alike, because on the moon, everything just rattles around forever because the moon is dry and broken up and seismic energy just bounces around. Also, the Apollo data was very limited by its digitization. They had about 7 bits of digitization compared to modern 24-bit systems. And so for the small events, they look more like barcodes than data. And so we're hoping to really move beyond that and deal with some of these challenges. So this is, I'm kind of fly through this because I want to leave time for questions, but these are the deep and circle and shallow and star events that are all mainly in the orange square, which is the near side, with a handful of events onto the far side. So we're really excited to look at that. And by being on the far side, hopefully we can also observe some of these near side events and constrain the deep structure of the moon. Schrödinger Basin is gorgeous. It's a beautiful crater structure with a peak ring. We're going to be landing on the northeast edge up here. And so we're looking to look at the structure under a beautiful impact basin and try to constrain impact formation processes. This is the VBB seismometer, once again, similar, it's supplied by Kness and actually using flight spares from InSight. Will be quieter than any of the Apollo instruments. And so we should be able to look at that noise floor and then use that to constrain the micrometeorite impact rate, which is pretty important for future habitation concerns. One of the big questions here was, I just showed you the InSight example and why we had to get on the surface and why that was all hard and very important. On Viking, we didn't do that, but the issue there was wind. Wind is terrible when you're sitting on a lander deck. There is no wind on the moon, so that's not going to be an issue. We are still coupled into lander noise, but you're also coupled into the ground signal. So, just to test that, we put a seismometer on the engineering model of Curiosity rover and on the ground right below it. And in the frequency band below the resonant frequencies of the lander, these see basically the same thing. On Earth, we did wonderful things until the air conditioning came on, actually. And once the air conditioning came on, we couldn't see much on the deck anymore because that's how sensitive we are to wind. But being on an airless body, we should be quite safe from that. But we will see lots of thermal cracks and pops, particularly at dusk and dawn. But the nice thing about the moon is away from dusk and dawn, it's pretty close to isothermal a lot of the time. Huge temperature swings at dusk and dawn, and it's going to be noisy as all get out then. But away from that time, we should have long periods of quiet where below the resonant frequency of the lander, which we have told the commercial landers they have to keep above 2 hertz. Below that, we should be able to see very good data. We're flying flight spare, very broadband seismometers from Paris. This is, but we're only going to fly one. So we're just measuring the vertical component on the very sensitive seismometer, but we will have 3 component sensitivity using the short period sensor, which is also flown on InSight. This is a new build, but it's based on the same design. This is going to measure the 3 component work. And so we're going to do the things like receiver functions with that. And a big part of our design is that this is a very innovative thermal design, which lets us keep operating through the night even though we're a solar powered mission. So we charge up our batteries during the day and then run on under 5 watts of energy continuous through the night. That still requires a big battery pack. It's about half of our volume and half of our mass is just batteries. But we're able to continue operating through the night and then do our communications during the day. So there's actually now just one antenna on top. This is an older figure, but so the solar panel is facing horizontally because we're relatively far south. So the sun doesn't get very far above the horizon. And then on top, we've got a radiator to keep us cool during the day. And the antennas, and then at night, we have some innovative insulation between these 2 cubes, which keeps us actually relatively toasty. We'll probably stay above 0 C through the night, which is, compared to InSight is warm and toasty. So this is a really exciting design. And so I went through this quick because I wanted to leave a little bit of time for questions. So the exciting thing here is we're going to the moon. We're getting data from the moon, which is exciting. The Apollo instruments were actually turned off in September of '77 when I was about 2 months old, and I've been literally waiting my entire life for more data from the moon. So this is very exciting. And we have some key questions. It's not everything we'd like to do. One of the interesting things, which I didn't have time to talk about, I actually cut out the slide, but we're actually flying with another heat flow probe and a magnetotelluric sounding system. So we're doing a lot of geophysics in one site from this commercial lander, the kind of things you'd like to do with the Lunar Geophysical Network. So this is a really exciting thing to attempt to demonstrate a lot of the geophysical approaches as we'd like to do in multiple locations on the moon in a networked form. So yeah, so that was quick. But I've still got a few minutes for questions, and I'm sorry to everybody, but I do have to leave right on the hour because I have NASA dumped a review on me while I was traveling, they changed the schedule. But few quick questions I can address.
Wonderful. Thank you, Mark, for this great presentation. Are there questions, especially if you are a young scientist, a PhD student, or a young postdoc? Now it's the time to ask your questions. All right, maybe I can start with a very quick one. Mark, based on the InSight results and on the experience that you gained with InSight, if you would have the opportunity to send another seismometer to Mars, where would you send it?
Yeah, so we've talked a lot about that. So one of the things I would be most interested in would actually be to send a small network of sensors to Cerberus Fossi, or potentially to some place in Tharsis where we've seen rock trails and are probably okay. But I would go Cerberus Fossi because we know it's active, and you can send a network by sending lower sensitivity seismometers that are lighter and cheaper. And since we already know there's seismicity there, we'd still be able to record it. So you don't need to fly the heavy sensitive seismometer. You can fly cheaper seismometers and then really look at processes in that area. I think that'd be a fascinating mission. But honestly, I'd be happy with any data anywhere. But if I were in charge, I'd probably put a little network around a known area and really focus on looking at the science there. I do see a hand up.
Yeah.
Hi, my name is Hui. Could you hear me?
Yes.
Yes.
Okay, great. I do a little bit, not mainstream seismology, it's environmental seismology. So I'm kind of curious, for the mission on Mars, do you guys record some kind of surface process signal rather than earthquake?
Lots of them. So we definitely are seeing atmospheric effects all the time. That pattern you saw in noise is really turbulence in the boundary layer. So we're recording that all the time. We actually have done a lot of work with looking at what the seismic. So we see vortices pass over, and we see them very clearly in the pressure sensor, but there's also a seismic signal from that. So you can actually get compliance measurements from that by looking at how the pressure change moves the ground. And so that a lot of our information on the very shallow structure is from actual atmospheric sources, not deep Mars quakes or anything like that. There's all sorts of interesting data of resonances. There are people in the mission that could talk about a 2.4 hertz resonance until your ears bleed. I'm not going to talk about that, but it's actually telling us stuff about potentially telling us stuff about resonant structures in the near surface. It's also potentially telling us stuff about resonant structures in the lander, which is why people will argue forever on it. But yeah, there's lots of other data in there.
Thanks.
All right. Any other questions?
Hi, may I ask a question?
Sure, go ahead.
Sure.
Yeah, thank you for the nice talk. I know that there are lots of going about denoising and development for the signal improvements in Marsquake data. I was also trying to denoise some of the Marsquake data, and I was wondering how people judge how this denoising affect the waveform for the Marsquake data.
Yeah, so before the mission, we thought we were going to do a lot of things like correcting for pressure effects, correcting for magnetic effects. In general, the only denoising we've used for most settings is removing glitches, deglitching activity. There's a paper led by John Robert Schultz that talks a lot about some of those approaches. A lot of different people in the group are working on that. And in general, that's pretty successful. It works pretty well. A glitch basically just gives you something that looks like the impulse response of the instrument to first order, and so they're relatively straightforward to remove, but they're not. It's not a perfect process. and you can actually introduce a little bit of noise when you do it. So it's helpful to look at different people's approaches to it. And if you're too aggressive at it, you can actually just remove all the signal, right? And so it's a really interesting process and a lot of work. But the really, as I said, the work that's been done has really focused on the glitches. Yeah.
Yeah. Thank you.
And I'm happy to talk more about it later, but I'm if people want to send me emails, I'm happy to talk more. Unfortunately, I do have to run. I hate doing this. I really will. I normally like to talk for about 15-20 minutes after a talk and just answer questions, but NASA calls and I must answer.
Well, thank you very much, Mark. This was really great, and I'm sure that if people have questions, they should contact you via email. I guess that's probably the easiest.
Yeah, email. I'm happy to take emails. I'm mark.p.panning@jpl.nasa.gov. So please email me. I get lots of emails, and so I may not respond immediately, but I will respond. I do promise.
Thank you very much, Mark.
Thanks, everybody.